Hello, I will talk about special relativity. There are three phenomena that occurs when someone is traveling at very high speed, close to the speed of light. The first phenomenon is the increase in mass. The second phenomenon is length contraction, and the third phenomenon is time dilation. I will start with the increase in mass. Suppose the twin brother who goes on a journey in space weighs 98 kilograms. So the weight actually is equals to the mass times g, and g is the gravity of Earth that equals to 9.8 meters per second squared. So the weight is 98 kilograms equals to mass times the gravity of Earth, that is 9.8 meters per second square. And when we divide 98 by 9.8, we get that the mass of the twin brother on Earth is 10 kilograms. Now I will explain the meaning of g equals to 9.8 meters per second squared. If you drop an object from the roof of a high-rise building, the velocity of the object will be 9.8 meters per second in the first second. In the second second, its velocity will be 19.6 meters per second. In the third second, its velocity will be 29.4 meters per second, and so forth. In the 10th second, its velocity will be 98 meters per second. In conclusion, every second the velocity of the object will increase by 9.8 meters per second. So when you will move in the spaceship at a speed of 80% of the speed of light, that is 240,000 kilometers per second, according to the mass increase equation of special relativity, is mass in space will be about 16.33 kilograms, but you will not feel it. Actually, if his twin brother has a mass detector, the detector will measure 16.33 kilograms. That means his mass has increased by 63.3%. So I will explain the question of the increase in the mass. M equals to m naught divided by the root of 1 minus v squared divided by c squared. M is the mass of the object when the object is moving at very high speed in the space, and m naught is the rest mass. That is to say, the mass of the object on Earth when it is not moving. And we divided it by the root of 1 minus v squared divided by c squared. V is the velocity of the object that is moving in the space. Okay, in our example, as we have already calculated, that the mass of the twin brother is 10 kilograms, and when we divided it by his velocity, that is 240,000 kilometers per second, and when we square it and divided by the speed of light squared, we get the result of 16.33 kilograms. So the twin brother in space, when he is moving at the speed of 240,000 kilometers per second, his mass will increase to 16.33 kilograms from 10 kilograms that was on Earth. Okay, so actually now we will talk about the second phenomenon that occurs when someone or something is traveling at very high speed in the space. Okay, the second phenomenon is called length contraction, or shortening the distance. When you measure a distance between two objects that are not in motion, then when they are not in motion relative to each other, and let's assume that you measure a certain distance so the distance between them will shrink if you measure the distance between them when one of the objects is moving towards the other object in very high speed. So I will explain the equation. L is the distance between the objects when one of the objects is moving towards the other objects in very high speed. L naught is the distance between the two objects when they are not moving relative to each other, and we multiply it by the root of 1 minus v squared divided by c squared. V is the speed of the object that is moving towards the other objects. So in our example, as mentioned, the distance from Earth to the star Epsilon is 10 light years when you measure it from Earth. But you should remember that our Sun is not moving relative to the star Epsilon, because the Sun and the star Epsilon move as one unit around the center of the galaxy, but the distance between them doesn't change. And suppose that my thumb is our sun, and the star epsilon is my finger, and my fist is our galaxy. So the stars are moving around the center of the galaxy. My fist is the center of the galaxy, and our sun and the star epsilon are moving around our galaxy, but the distance between them is not changing. They are moving like this. Okay? So in that situation, actually we measured the distance between Earth and the star epsilon when they are not moving relative to each other, and in that situation we get that the distance between the spaceship and the star epsilon is 10 light years. But when you measure the distance from the spaceship that moves in the space at the speed of 240,000 kilometers per second, then the distance will be shrinked to 6 light years only, from the point of view of the twin brother flying in the spaceship. So actually we use that equation in order to calculate what is the distance between the spaceship that is moving in the speed of 240,000 kilometers per second between the spaceship to the star epsilon, and actually we get the result of 6 light years. So the distance between Earth and the star epsilon shrinked from 10 light years to 6 light years only. And there, of course, the v is the velocity of the spaceship that is moving towards the star epsilon, and c is the speed of light. So we see that the distance between Earth or the spaceship to the star epsilon, the distance is shrinked by 4 light years, from 10 light years to 6 light years only. So that phenomenon is called the contraction of distance. Okay, so when you have two objects, that one object is moving towards the other object in very high speed, the distance between the two objects will be shorter than the situation when you measure that distance between that two objects when they are not moving relative to each other. Okay, in our example, we see that the distance between Earth and the star epsilon shrinks from 10 light years to 6 light years because of the fact that the spaceship is moving towards the star epsilon in very high speed. Okay, so that phenomenon is called the contraction of distance. Okay, but in addition to that, the height of the man in the spaceship also shrinks. And if on Earth his height is 1.8 meters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spacecraft shrinks to only 1.08 meters. So if the twin brother that stays on Earth had the height detector, then the detector would show a height of only 1.08 meters. But the twin brother who is in the spacecraft doesn't feel that he is shorter. Okay, so I will explain the equation. So it is the same equation as the contraction of distance. Here is actually the equation of the contraction of the length of the height. So L is the height of the twin or something or someone that is moving in the spacecraft at very high speed, and L naught is actually the height of the twin brother that is on Earth. The height on Earth of the twin brother is 1.8 meters, and we multiply it by the root of 1 minus v squared divided by c squared. V is the velocity of the man that is moving in the spaceship. In our example is 240,000 kilometers per second. We divided it by the speed of light squared. And the final result that we got is 1.08 meters. So we see that the height of the man that is in the spacecraft and moving in very high speed is actually shortened from 1.8 meters to 1.08 meters only. So it's actually shortened by 72 centimeters. So if the twin brother that stays on Earth had a height detector, then the detector would show a height of only 1.08 meters. But the twin brother who is in the spacecraft doesn't feel that he is shorter. Okay, now I will talk about the third phenomenon that occurs when someone or something is moving at very high speed in the space. The third phenomenon is time dilation. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship the rate of the time flow in the spaceship will be slower than the rate of time flow on Earth. While on Earth it took 25 years for the twin brother to return from a journey in space, in the spaceship the total time that it passed is 15 years only. So I will explain the equation of time dilation. T is the total time that passed in the spaceship that is moving in space at very high speed, equals to T naught. T naught is the time that is passed on Earth during all the journey of the spaceship until the spaceship returns to Earth, and we multiply it by the root of 1 minus v squared divided by c squared. V, as I already said, is the velocity of the spaceship. We square it and divided it by the speed of light squared. Yes, so in our example, the total time that is passed on Earth during the journey of the twin brother in the spaceship towards the star Epsilon and back from star Epsilon to Earth, the total time that is passed is 25 years. And when we multiply it by the root of 1 minus 0.8 squared, we get the 15 years. That is the total time that is passed in the spaceship. So we see that the total time that is passed in the spaceship is 10 years less than the total time that is passed on Earth. Yes, while from the point of view of the twin brother who embarked on a space journey towards the Epsilon star, he is at rest and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation, there will be a contraction of distance according to special relativity, and the total distance between Earth and the star Epsilon will be 6 light years only, and the round trip distance is 12 light years, and at the speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to the contraction of the distance between the spaceship and the star Epsilon as mentioned. So actually, from the point of view of the twin brother that is on the spaceship, he is at rest and the star Epsilon is moving towards him at the speed of 240,000 kilometers per second, and in this situation there will be a contraction of distance between the twin brother that is on the spaceship to the star Epsilon, and the distance between the star and the twin brother will be only 6 light years. It is 4 light years less than the original distance that was 10 light years, and the total distance back and forth is 12 light years, and when you divided it by the speed of the spacecraft, that it is 80% of the speed of light, we will get 15 years. So the total time that is passed in the spaceship is 15 years only. The same result as we got when we calculated the total time that is passed in the spaceship from the point of view of the twin brother that stayed on Earth. Okay, thank you very much.